Hello and welcome to the second part of our discussion on, oops, I just bumped my computer, oops, on statistical inference, specifically starting the discussion on hypothesis testing. Now we're going to do this by way of a few examples, and hopefully by seeing enough examples, slowly it'll sort of fill in the picture and the reasoning we go through in the basic hypothesis testing method. As we progress, it will get refined a little bit to be a little bit more realistic, but this template that we'll focus on today is a good starting point to get the idea and to start visualizing by way of a graph what is happening here. So we have a couple of examples. Let's look at this first one. Now, to not distract you, I'm going to hide it a little bit lower so that we can all read the same thing together. I don't think I can make it much bigger. It's too big if I zoom in. See, it's hiding a little bit. Might be okay. I think it's just okay. So let's read our intelligence example. A person claims that she can identify people of above average intelligence with her eyes closed. It is known in advance that the distribution of intelligence in the general population is normal with a mean of 100, standard deviation of 15. The woman's blindfolded, taken to a stadium full of randomly selected people, and chooses someone with an IQ of 140. Could this result have occurred by chance? Or a better question is the stadium truly full of randomly selected people that represent the population? Because the population mean the average intelligence quotient is 100. She now picks from this stadium and selects someone of IQ 140. So what we can do is split this up into essentially two groups that we'll call two populations. Population 1, the people chosen by the woman with her eyes closed. Population 2, the general population, people she didn't select. And then we essentially want to figure out the following. Now, I'm going to hide a little bit of this. The research hypothesis, I view it as sort of what I want to believe, but I don't know if I can. I want this to be the eventual conclusion. I'm just not sure. So I let the evidence help me make that decision. And my research hypothesis in this case is going to be population 1, people chosen by the woman, will be more intelligent than population 2. That's her claim. That's what she wants to be true. Are people selected by her more intelligent than people in general? That would sort of prove her claim, she hopes. That stands in contrast to what we call the null hypothesis. I think I have some space here, which will be the opposite. Now you can do the null hypothesis first and then the research hypothesis. It doesn't really matter for me. They sort of go together and they are opposites of each other, loosely speaking. The null hypothesis is then population 1 rather, will not be more intelligent than population 2. People she selects will not be more intelligent than people in general. Now, of course, there will be some variation in the IQ of people you select, regardless if you're skilled or not, like this person claims. So even though the mean is 100, The standard deviation indicates that you're going to get numbers around 100. Most of the time, 15 above, 15 below in that range, but of course, further out has a chance of occurring as well. So we need to keep that in mind. So what we're going to do is look at the distribution that they suggest here. Normal distribution, mean 100, standard deviation 15. And then we're going to ask, well, how likely is it that she would just randomly, without skill, select someone of an IQ of 140? So then we need to see the distribution, and we need to ask ourselves, well, of course anything is possible, but within reason. So we're going to choose what we call our significance level, and we're going to represent that by an alpha of, well, that's going to be a percentage. Now you can say 5%, or you can say 0.05. It's the same thing, right? Just a decimal version of the percentage. Usually we choose a 5%, sometimes a little more, sometimes a little less. You have to make that decision because everything is possible, but not likely. You're going to say, well, okay, let's look at this graph. Zoom in a little bit here. I'm going to look at this top 5% and say, oh, it's right there as well, 5%. If she is just randomly selecting with no skill whatsoever, she could get anything in the IQ range. Fair enough. But there is only a very small chance that she's going to get someone in the top 5%. Most of the time, if you just randomly select someone, you're going to get a whole range. And we saw the regions before, right? This region over here, and then it drops off the further out I go by my standard deviation steps. So it's much, much more likely to get someone within a certain range around the mean. So we make a decision and say, okay, we view the top 5% as being too rare to just randomly stumble upon. That is a decision we have to make. We have to cut it off somewhere. So this is our cutoff. Otherwise, anything is technically possible, right? So this is how the system works. So in our comparison distribution, we make the decision. I didn't write that. There we go. There we see the 0.05. I can zoom out, I guess. To determine a cutoff for the sample score or a critical value on this distribution of how IQ scores in general behave. So if we choose 5%, which is very reasonable, we can calculate based on our mean and our standard deviation the corresponding z-score that is needed to have the top 5, to be at this top 5% line. How do we do that? Well, let's go to our table, and we're looking for the tail, 5% in the tail. Okay, so I'm going to have to go way down. I'll slow down once I get there. 5%. Where are you? 5%. I'm coming up to it. Now again, there is some flexibility here. Where's 5%? I just missed it. There we go. That 5% is technically right in between these two. But just for the sake of being consistent with books you might see, I would take the average personally, But in this case, let's just be a little bit more aggressive and go on the higher side as 1.64. Regardless, you get that in your table. So it's a decision you make. Say, well, I don't want to be, if I only want to pick numbers from the table, I don't want to be making it more than 5%. So I'm going to go a little less. So it's actually a little less than 5%, that cutoff line. So that's how I choose the corresponding z-score for my cutoff. I can then also say, well, what is the actual IQ score that matches this, that corresponds to this 1.64? Well, we saw that last time. You put in the z-scores, standard deviation, mean, and you get 124. So these two are equivalent for this discussion. If you look at in a table, well, you have to do the standardized version. But if you're talking in the context of this question, well, then you can talk about actual IQ scores. So let's just think before we reveal this. What does this mean? So 124.6, we got there. So these two are interchangeable depending on how we want to talk about these things. So in the general population, anyone with an IQ score of 124.6 is in, roughly speaking, the top 5% based on this distribution. So if you didn't have any skill and you were just randomly choosing a person, then you would have a 5% chance only of selecting someone with an IQ above 124. So the chances, it's much more likely for you to get someone below 124.6. If you just randomly select one selection, and I get an IQ of 140 as my selection, puts me over here. So we'll call this the observed score. That can be viewed as being so rare that there must be something to your claim to just in one go select someone with a probability that is that small. So our cutoff that we were happy with viewing as rare enough was over here. What she actually, was it a she? I can't remember. I think so. Why does that bother me? No, just a person. Oh, she, yes. What she actually ended up selecting was even further out, even more rare, just adding to the strength of her claim. The evidence is actually stronger than we would have been okay with something over here. A 125, that's still rare. She got a 140. That's even better, even stronger evidence. Okay, so that's the idea here. So let's wrap this up. So we determined the sample, the score that she got as a sample, the sample score, 140. Now, you have a choice here. I mean, these two are interchangeable. You can convert it to a z-score. So if you want to compare z-scores, you would have to convert it, of course. If you want to just compare raw scores, IQ scores, then you could do that. You choose. It really doesn't matter, right? So we're listing both here, but you don't have to do both. So we have to now decide, is this strong enough evidence to make a conclusion? So the null hypothesis was really sort of the assumption. If we go on the assumption that the people she selects are not more intelligent than people in general, meaning we assume she has no skill. So this is our assumption. We assume she has no skill. That's what the null hypothesis says. We then look at the evidence. What does the evidence suggest? Well, she just selected someone that would be very rare to just get if you have no skill. So this suggests that the null hypothesis is not true. And there is more to it. Because to randomly get someone that is that rare, it's unlikely. So we're sort of playing the odds in a way, so to speak. So the raw score is more extreme than our cutoff score. Cutoff. The corresponding z-score is more extreme than the z-score. You only need one of these. Where can I write? I'll write over here. I only need one of these. I don't need both. But for the sake of giving you options, we have both. And we therefore conclude, or therefore make the decision, to reject the null hypothesis. That it's too rare. It can't be true that what she selects is the same as the population. There must be more to it. Now, we never accept the research hypothesis. We never accept that she has a skill. All we can say is there is sufficient evidence to suggest that the null hypothesis is not true. There is strong enough evidence. That's better, not sufficient. Strong enough evidence to suggest that she may have something. However, we can't say that she does, because there is a chance, however small, if you just randomly pick someone from the population in general to get someone with an IQ of 140. You always have a chance. So it could have been a fluke. So we can never say that this proves that she has the skill. We can only say that we have strong enough evidence to reject the fact that she has no skill. So there's a subtle difference between the two. We never accept the research hypothesis. It's not an example, doesn't serve as proof, but it can serve as evidence against something. So we'll get used to that as we go. Okay, so let's look at another example. I'm going to leave it small in this case. Lottery example. A study is done in which a randomly selected person, this looks so small now. I'm used to the big one now. We could fit it in just, sure, why not? Study is done in which a randomly selected person is given $10 million. Why not? The person's happiness measured 6 months later is 80, whatever that score is based on. It's known in advance that happiness in general in the population is normally distributed with a mean of 70 and a standard deviation of 10. Could this result have occurred by chance, or does the evidence suggest that it could be connected to this $10 million? Let's explore this. So I don't want to show too much. Let's go with that. So we have essentially two groups here. People who 6 months ago received $10 million, and this random person is one of those selected from population 1. But of course, it could have happened to other people as well, because we want to say something about people that receive $10 million in general. But the population 2 will then be just the general population, people that didn't get this amount of money. What we're interested in finding, we're hoping that population 1 will be happier than population 2, or the average happiness score will be more. And the null hypothesis is that it will not be. So we'll assume the null hypothesis is true. Assume this is true, and then explore what the evidence suggests. Now our comparison distribution is going to be the normal distribution, mean 70, and standard deviation 10. Let's visualize. Let's visualize this. Ooh, blue. So there's the distribution centered at 70. I'm going to choose my 5%. Now, if I want to have, if I want to make sure the evidence is super strong, I can change that to a 1%. If I don't care as much about my decision, I can relax this a little bit and make it 10%. 5% is sort of in the middle, very often used. So what does this 5% mean? It means that in this distribution of happiness scores, there is only a 5% chance of getting someone beyond this cutoff line. Now I can do that in terms of the happiness score, or I can do that in terms of the z-score. We already looked it up. We know that whatever that happiness score is, it corresponds to a z-score of 164. So the benefit of the z-score is that I have some consistency from one to the next, even though the actual raw scores can be a whole bunch of things, right? So that cutoff line is 1.64 in its standardized form. Okay. So this now is the approach now is going to be, so let's see what we get from our observed sample. Well, we got a score of, I believe it was 80. So we determined the cutoff. You can choose, do you want to go z-score? Do you want to convert it back to the raw score? We'll do both. Give you options. You don't have to do both. So my sample score is 80. I can now choose. Do I go raw score, z-score? Decide. If I do the raw score, the happiness score, I compare it to my cutoff of 86. So this one over here was 86.4. Let's write it over here, 86.4. We got a score of 80. This is the observed score. So what does that mean? Or what does that tell us? Whether I say 80 versus 86, or whether I convert it to its z-score, in this case 1 versus 1.64, the information is the same. But if I talk about happiness scores just for convenience, this means that I am very likely to get a happiness score of 80 in the general population without having the $10 million. A score of 80 is not rare. It's quite common. I have a range around 70, my mean. That could happen if I just randomly pick people. Some will be 75, some will be 70, but a lot of them will be 80. Some will be 85. But I decided my cutoff for considering a score to be quite rare and something I won't get often to be this line over here. So my observation falls within that line, not in the tail. So I can say that the evidence is not strong enough to suggest that the $10 million has a significant effect on happiness, because I got a person that I could have just gotten randomly anyway. Their happiness score wasn't very extreme. So we can say the evidence isn't strong enough. So let's sum that up. So our score, whether I do z-scores or the x scores, I can say that it's not more extreme. It's actually quite common to get that score. So there isn't sufficient evidence, or isn't strong enough evidence, to suggest that the $10 million has an effect on the happiness score. So therefore, we do not reject the null hypothesis. It's inconclusive. We can't say. The null hypothesis was that they're not happier. we got evidence that doesn't really contradict that, doesn't suggest that it's not true. We can't say that the research hypothesis is true or false. We can only say whether we received strong enough evidence to go against the null hypothesis. So be aware of that and be aware of the decision. We either reject the null hypothesis because the evidence is considered to be very strong and wouldn't just happen by chance. So something is actually different than what our null hypothesis assumption is. Or we do not reject the null hypothesis. The evidence is not strong enough, and we could have just gotten it randomly anyway. It doesn't suggest that anything else is happening. The evidence in this case doesn't suggest that people who got $10 million will be any happier. We got a person we could have just gotten anyway. All right, so our conclusion is always sort of phrased in terms of the null hypothesis, the evidence and how it compares to the null hypothesis. Definitely draw a picture. It definitely visualize what's happening. It helps a whole bunch. Now, of course, you can pause and think about it, but in this video, we'll just continue. Let's zoom it in again. Let's go over here like so. It's so close. There we go. Stress reduction example. A health psychologist wants to test the effectiveness of a new stress reduction method. In the general population, stress level is normally distributed with a mean of 40 and a standard deviation of 10. A randomly selected person is trained in the method to reduce their stress, and the person's score after this training is 25. We want to know, essentially, is the evidence suggesting that perhaps this training reduces your stress score, or stress level rather. Okay, so we have two groups of people trained in the stress reduction method and everyone else. We want to know, is it actually better? Is the stress reduction effective? Did the stress level go down? So the research hypothesis I view as sort of what I would like to have happen. I would like the conclusion to be that the average stress is actually less. And the null hypothesis is the opposite. All right, so let's see what our comparison distribution is. Normal distribution, mu 40, sigma 10. Let's visualize that tab. In this case, however, we expect or want to investigate the less than. So the score, we're trying to investigate if the scores are lower by way of this training method. So we are working with the left tail in this case. Now, just to mix things up, let's choose a different significance level, a different alpha. Let's choose 1%, for example. We then look at the table. We can go and find that on the table. 1%. Where are you? 1% over there. Closest one is 233. Now that's the right tail. We just flip it. Symmetry, negative 2.33. So that's where we get this guy. Then we can calculate the corresponding score if we want to talk about the stress levels or talk about the z-scores. It's the same thing, right? So we want to be comfortable and flip between them as we want to, because they are equivalent. So what does this mean? This means that now I chose an alpha of 1% because I don't want to be too fast in saying that the stress reduction training works. I only want to start suggesting or start thinking that it might work if the evidence is really strong. So I want stronger evidence in this case. That's a decision I make beforehand. I don't want a 5%. I want it to be a little bit stronger before I not accept that the stress reduction method works, but before I not reject it, so to speak. Because maybe there is a lot of money involved to go ahead with the training, to develop this procedure. Maybe it's a whole thing, and I don't want to make that decision lightly. So we decide on a 1%. So that means that I'm going to view it as fairly common to get stress levels above this line. They're not going to be at 40 all the time. Some will be lower, some will be greater. And I'm going to view this range as common. If the stress reduction method doesn't work at all, I could still get some random fluctuations. It doesn't suggest anything necessarily. So now we look at the score that oops, that's the wrong tab, sorry. Look at the score we got, which was 25. So we determined the cutoff with a 1%. We got a 25. Now we can convert that to a z-score, or we can just compare the 25. Totally up to you. What do we see? We see that 25, the observed score is over here. That's not strong enough evidence to suggest that the stress reduction method actually lowered the stress level, because it could have just happened randomly. Unfortunate. But I keep clicking on the wrong tab. What's wrong with me? There we go. So we make our decision. Let me just scroll like this. The score, z-score or raw scores, whatever you want, is not more extreme than the cutoff score. So it's not a matter of if it occurs to the left or to the right. It's a matter of if it's more extreme or not, right? Because it can be on either side. It depends on the situation. Sometimes I have the right tail, sometimes I have the left tail, and it's a question of being more extreme. Therefore, I do not reject the null hypothesis. The evidence is not strong enough to suggest that something else is going on here. The null hypothesis that population 1 with the stress reduction method will not have a lower stress score, I don't reject it, because I just got a person randomly that took the stress reduction method, and it wasn't really extremely less to suggest that this works, or even if it does work, even if it maybe does work, its effect could be so small that I don't really even notice it, and it's not worth investing in. But I was hoping to get something really low. Then there's a significant drop in the stress reduction. Strong evidence to suggest that this might work, but that's not, unfortunately, what I got. So I can't reject the assumption that it does not work. So the point here with this example, you have to go through the process again, and you'll see the same words and the same thinking come up, but you just see something that has left tail as well. Now, in certain cases, in this one, we were quite confident, for whatever reason, that scores will only be lowered by the stress reduction method. And that's the only test we need to worry about. But in other cases, we might not know. We might want to test it whether it goes up or down, just whether there is change from the population 2, or we might actually not know which way this treatment goes. Could be better, could be worse. So in the one-tailed case, can I zoom? That's big enough. In the one-tailed case, we only worried about one side because we knew more about it. We knew what to expect. It was just a matter of how strong the evidence is. But if we didn't know anything, we're going to have to split up our 5% and make it a two-tailed test. So 2.5% will be in the right tail and 2.5% will be in the low tail, in the left tail, sorry, high, low, left, right, whatever. So in that case, I'm looking for a 0.025. Let's see our table, 0.025, sorry, 2.5, this is in percent. 2.5%, where are you? 2.5, there it is. 1.96 for a 5% alpha. 1.96. Of course, if you compare that, because we're splitting it up, we don't know which way to go. The cutoff is going to be a little further out. But it's the compromise to cover both sides when we don't know. Now we could, of course, do a 1% significance level as well. And that just moves the cutoffs further out. I could look that up just like we did the 1.96. So let's have an example of this situation. See if I can zoom in nicely again. It's good enough. All right, depression example. Clinical psychologists developed a new type of therapy to reduce depression. However, it could make the depression better or worse. They don't know, and they want to explore this thoroughly. They don't want to assume anything. The psychologists randomly select an incoming patient to receive the new form of therapy instead of the usual. After 4 weeks, the patient scores 41 on a standard depression scale. For those who receive the usual therapy, their depression after 4 weeks is normally distributed with a mean of 69.5, standard deviation 14.1. We want to see if there is a change. We don't know, up or down, up or down. So population 1, patients who receive the new therapy. Population 2, patients who receive the general therapy, the usual therapy. We're hoping that there's a difference. Research hypothesis, sort of what we hope, right? But, and the null hypothesis is the opposite, that there is no change. And the true population mean between the two therapies is actually the same for the depression level. Just because I found someone that has a score, where is it? There, 41, different from the mean. Well, I'm not going to get the mean exactly. There's going to be fluctuation. That's what standard deviation really says. But how far away from the mean is far enough to suggest that maybe the people who receive the therapy do overall have a lower or different depression score. Depression score, is that right? Yeah. All right, so our characteristic the comparison distribution has a mean and a standard deviation, like we said. So we'll picture this and say, well, let's assume that the means are the same as the usual therapy. Everything is the same. Now I get a person. Well, sorry, before I actually get the observed person, I decide on my cutoff as 5%. Alpha is 5%, 2.5 in either tail, because I don't know which way this is going to go. Hopefully not worse, but I don't know. I'm trying to investigate it. So my cutoff score there is 1.96, as we saw before. You can convert that to the corresponding raw score. That will be not sample. Oh, we didn't do that. I think we did it on the table here as 97.7, but you don't need it, right? We could just use the z-score in this case, 1.96. So we want to know, okay, well, if we get a sample from the new treatment, and it's out here or out there, we can see that as strong enough evidence to suggest that this new treatment group population actually has a different average depression score, because we wouldn't just randomly get this extreme. We would usually get them in here. For us to just randomly select someone from the other treatment and get a score that's extreme, that is going to be considered strong enough evidence to suggest that something has changed. So what do we actually get? Well, I'm going to have to go look. No, that's not it. Nope, that's not it. This one. So determine the sample score on the comparison distribution. Well, we got a score of 41. Z-score is negative 2.02. All right, let's look at the graph of that guy. Negative 2.02. Ooh, that is close. But it is a little to the left. It is in the what we consider extreme area. It's not super strong, but it is strong enough to suggest that there is a different underlying average score for the group with the new therapy. It is slight, but that's why we have a cutoff, to make this decision black and white. I keep clicking on the wrong slide. What is wrong with me today? I do not know. So we make our decision. The score at step 4, the observed score, negative 2.02, is more extreme than the cutoff, negative 1.96. Therefore, we reject the null hypothesis that said things are the same. It doesn't matter. The different therapies are the same. We reject that, because if they were the same, we would not get something this extreme. The research hypothesis is supported. We're not saying it's true. We're not accepting it. We're saying things are not the same. And the evidence supports the possibility that the research hypothesis, that things are different. We don't know if it's true, because there is always a chance to get something randomly over here. There's a chance. But we just consider that so rare. A sample doesn't prove the research hypothesis, but it can contradict the null hypothesis. There is a difference in the logic. Patients receiving the new therapy, the evidence suggests we should say it like this. We can never say patients receiving the new therapy have different depression level. No. The evidence suggests My pen is a little thick today. That the new therapy have different depression level. We will never truly know. But the more evidence we collect, the more this situation happens, the more convinced we'll be, I suppose. All right, let's wrap it up with one more. The more examples we see, slightly different yet the same, the better off we are. Now, this might happen too fast for you, jumping from one to the next, but you can always pause the video, right? Pollution. Does pollution affect the amount of sleep you get? A person living in a polluted region was randomly selected. His sleep the night before was 10.2 hours. In general, the population in general, amount of sleep is normally distributed around 8, standard deviation of 1. So let's look at the two groups, people who live in polluted region, people who do not. And we are trying to see if the amount of sleep is different. We don't know which way. Does it cause more sleep? Does it cause less sleep? We don't know. And the null hypothesis is that it's exactly the same. There's no effect. So our comparison distribution, like they said in the question, let's visualize. Actually, what alpha are we doing? 5%. Okay. Can't remember. Let's visualize what's happening here. Well, we have our 2.5%, 2.5% on either side, familiar cutoff of 1.96 and the negative, of course. So those are the cutoffs. We don't necessarily need to know what the sleep hours is that those convert to, right? So we're going to say, well, if we now observe an amount of sleep that is past these extreme cutoffs, we consider that so rare, we wouldn't get that just testing a random person. There has to be something going on here. Let's see what we got. We got a sample score corresponding to 2.2 in the z-score. Let's visualize 2.2. Oh yeah, for sure, that's over here. Z observed 0.02, right? That is more. Not, was it 0.2 or 2? I'm thinking of the previous one. Yeah, right. The previous one was 2.02. 2.2. Still not a lot, but it is in the past the cutoff, in the zone that we view as too rare to just happen by chance. So we base our decision accordingly. And we can say that the score, z-score 2.2, observed is more extreme than our cutoff of 1.96. Therefore, we reject the null hypothesis. Now let's remember what it did say. Null hypothesis was no effect, no change. We reject that and say the evidence is strong enough to suggest that there is a change. We don't know if there is, but the evidence suggests that there is. There's a difference. There's a difference between saying there is and saying the evidence suggests that there is. So I want to update this sentence here. The evidence suggests that people living in polluted areas sleep a different amount than people in general. We will never know if it's true, but the more evidence that suggests this, the more we will start to think that it is. So pay close attention to how things are said. I will never say the research hypothesis is true. I will simply say there isn't evidence to say it's not true. There's evidence to suggest it might be true, but we never commit to saying it is true. That is important. All right, so with this, I'll end with a diagram. Blah, there we go. With this, we hopefully get the basic idea and thought behind hypothesis testing. We'll slowly refine it and talk about it in slightly different ways, but the basic template, the basic steps in that thought process will be the same. All right, until next time.